Welcome back, everyone. In this week's lessons, we're going to be talking about a lot of different chemical reactions and starting to move away from our understanding of atomic theory. Our understanding of atomic theory will help us in a lot of different ways, especially when it comes to understanding redox chemistry. But what we're going to do today is learn about 5 different types of chemical reactions, and I'll give an example of a variety of those. And then we'll talk about nomenclature of polyatomic compounds as well as acids and hydrates. Um, and I'll begin with this diagram here, which is a breakdown of these 5 different types of reactions. And this is one way that chemists tend to classify reactions. So when we look at this diagram, we have A and B, which can be either elements or compounds. So let me just make sure I write that down. These can be elements or they can be compounds. And when I combine 2 elements or 2 compounds together and I get one new compound, we call this a combination or a synthesis reaction. And if we go on to take organic chemistry later on, a lot of the types of reactions that we'll be interested in are synthesis reactions. Now, there may be a side reaction that occurs in a synthesis reaction, but what we're interested in is this compound that forms between A and B. And then opposite of that is a decomposition reaction where we have some compound that's bound together between elements A and B, and then that compound breaks apart into simpler elements or simpler compounds. And this doesn't have to be, so these ones here, A and B, these don't necessarily need to be a pure element. They could be a diatomic compound. But it will just be composed of A or just composed of B. And I'll show you a variety of these and we'll practice this. And then the next type of reaction is a single replacement. So here we have to have 3 different types of elements. 2 of them will be bound together, and this doesn't necessarily need to be a covalent compound. It could be an ionic compound. And in most of the situations, it will be ionic, where A will displace usually the cation of the ionic compound. So A will displace B, and then you'll form a new compound between A and C. And A and B are generally going to be metals. It could also be the polyatomic ion ammonium, or it could be hydrogen. And then C is generally going to be a polyatomic ion or another metal. Or, sorry, a nonmetal. We'll talk a lot about polyatomics again today. So you may have read ahead about that. Nonmetal. So this is just a classification scheme that we're going to be using. And then double replacement is where instead of just switching one, we displace 2 different metals. And we can see that, like in this situation, A and C just change partners here. So we form a compound between A and D and B and C. And we'll note that we're going to keep the names of the compounds where the metal is always first, and then and then the latter part is always the nonmetal or the anion. So we're switching the cations here. So we're going to assume these are ionic compounds. So assume, for most cases, these are ionic compounds. And then the last type of reaction I like to classify separately. It could also be considered a combination reaction in certain circumstances. But those are combustion reactions where we have a compound that's composed of carbon and hydrogen that reacts with oxygen. And in this reaction, we're going to get heat and we're going to get fire that's produced as well as light when we break the bonds between carbon and hydrogen to form new carbon-oxygen bonds in the form of carbon dioxide. And we'll also get water vapor as another product. So whenever we have a combustion reaction, if it's something that says it's combined with oxygen, we're always going to get carbon dioxide and we'll get water as a product. And we'll also see fire as a result of that too. There are other types of combustion reactions that don't involve carbon. You can have a combustion of a nitrogen-based or a sulfur-based compound as well. And if you read in the textbook, this week we're reading through chapter 10, you may see some of those types of reactions as well. All right, so let's go and look at some of these example types. But real quick, if you see something that has the formula C, carbon and hydrogen, I'm going to be classifying these as organic compounds. And if it's ever reacted with oxygen, we know we're going to have a combustion reaction, and CO2 and H2O are going to be our products. Unless there is a different type of compound. So unless it's a nitrogen or sulfur combustion. All right, cool. So let's look at this first example here. And this one, if we take a strip of magnesium and we combine it with oxygen and some heat, so we're going to need some heat to drive this reaction forward, we can get a synthesis product, a magnesium oxide product. So whenever we have a metal and oxygen, we'll form an oxide as a result. And there are no other products here. You might notice that this reaction is not balanced. So if you caught that, that's very good. So let's go and balance this reaction. We're going to need 2 magnesium oxides so that the oxygens are balanced. And then we'll need to balance the magnesiums on the left side. And this type of reaction is really fun because if you burn magnesium, you're going to get this really bright white light. It can be quite blinding, so it's not a good idea to look at it directly, but everyone does for show. And that's our simplest example of a synthesis reaction. For an example of a decomposition reaction, if you hook up water to 2 electrodes and you place an electrolyte in the water, so something that can conduct electricity better than water. And on one end, we can get the production of hydrogen gas, and on the other end, we can get the production of oxygen gas. This is a type of electrolysis experiment where we decompose water, which we know is a pure compound, into its pure elements, hydrogen and oxygen. So when I write this, in the elemental form, we'll have hydrogen, and it breaks down into hydrogen gas, which is H2, and we'll get oxygen gas, which is O2. Let's go ahead and write the states of matter for all of these today. So water is a liquid at room temperature, and then hydrogen is going to be a gas at room temperature, and so is oxygen. And then in order for this to be balanced, we're going to need to have 2 waters break down into 2 hydrogen molecules and 1 oxygen molecule. And when we look at this diagram on the right, we can see that one of the tubes of gas is smaller than the other. That's because this here is the oxygen that's being produced. And then here's the hydrogen that's being produced. So one thing about gases that we're going to talk about in lesson 18, we're going to talk about how, is it 18? That's why. Okay. Yeah, 18 and 19. We're going to talk about, where was I? How equal volumes of gases will be equivalent to equal moles of gases. So despite oxygen being a more massive molecule in the sense that its mass is heavier, it will occupy the same volume per mole that hydrogen does. So that's an interesting thing we can see here. And if we go back and look at this diagram, the decomposition reaction, AB, so here we have A being hydrogen, for example, and O being oxygen. So this compound could be composed of more than two elements, breaking down to simpler compounds, A and B. So just a compound made of A and just a molecule made of B. All right, so here's another fun experiment that we've done in our course. So in 111 lab, we took Epsom salts and we put them in an oven to dry them. And when we did this, we dehydrated the Epsom salts to give us a salt and water that evaporated off. And we were able to determine the formula. And many of us were unable to remove all of the water. And part of this has to do with the fact that we just weren't getting it hot enough. The oven is great at creating a dry environment. But the best way to remove water from a hydrate is to place it under a Bunsen burner, as shown here. And this is an experiment you can do if you have the right setup. So what we're going to do here is we need to write out the formula. So magnesium is Mg, and then sulfate, we'll learn about the naming of this in a little bit, but this is a polyatomic ion, and it has the formula of SO4, and it has a 2- charge. So magnesium sulfate is MgSO4, because the charges will cancel, and it's a heptahydrate, meaning it has 7 waters of hydration per formula unit. When we dehydrate the compound, we're going to end up getting magnesium sulfate, which is the anhydrous salt. And then we'll get water. So here's a different example of a decomposition reaction. All right, so here we're going to break this down. We'll get MgSO4, and this is a solid. MgSO4 is also a solid. Sorry, it's been a few days. I got to get used to writing again. MgSO4 is a solid, and then water is H2O, and there should be 7 of them. And when we heat it, it's going to come off as a gas. All right, one of my favorite types of single replacement reactions are ones that we can visualize. If we take a strip of zinc and we place it in a solution of copper sulfate, the copper will be more active than the zinc and will displace the zinc coating from that strip and deposit itself on that strip. And then what we'll end up with in the solution here is zinc sulfate. And zinc sulfate is going to be colorless, whereas copper sulfate is blue color. So over the course of this reaction, you can see the depositing of this copper metal, and you can see that the copper ions are being removed from solution and being replaced with something that's colorless. It's still a little bit colored here because the reaction's not done. So putting this in a word formula, it could look like something like this. When zinc is placed in a solution of copper 2 sulfate, it yields copper and aqueous zinc sulfate. So here we're assuming the zinc here is a solid, and whenever it says a solution, then this is going to be an aqueous compound. An aqueous compound is something that's dissolved in water. And then copper, it's going to yield as a solid. And then we're going to have aqueous zinc sulfate. So specifically says aqueous here. So let's go ahead and write this formula out. We have zinc and copper 2 sulfate is given the formula CuSO4. Again, sulfate is SO4 2 minus, and then copper 2 would be Cu2 plus. And then we're going to get some copper, and we're going to get zinc sulfate. And zinc is always has a 2 plus charge. And so in this one, we don't need to balance the reaction. It's already balanced here. And when you go and you're reading through chapter 10, we'll talk about the activity of metals, which I'll talk more about in lesson 15. But there's another thing that can happen in a single replacement. Instead of a metal here, so this is a metal, and we have an ionic compound where we have a metal and a polyatomic. We can have a type of compound where there's instead, we can have hydrogen. So we can add, we could also do an acid. So we could have a metal plus acid. So that's a different type of reaction. Or we can have a metal, we can have a halogen with another halogenated compound. And these are 3 types of single replacement reactions. So here's 1, here's 2, and then here's 3. So if I take the halogen chlorine and I bubble it through a solution of sodium bromide, I can displace the bromine and replace it with chlorine, because in the activity series that we'll learn about, chlorine is more active than bromine is. And so you'll see, we'll see is that as we go up on the periodic table, the halogens become more and more active, and chlorine is above bromine. So what we'll end up getting for this is bromine that will be displaced, and we'll get sodium chloride. And we want to practice writing this in the formulas. Chlorine is a diatomic, so it would be Cl2. And in this situation, chlorine is typically a gas. We can also get it into an aqueous form. This image here on the right, all of these halogens are actually aqueous to begin with. And then we'll have sodium bromide. This will be a very weak solution. And we'll end up getting bromine, which is Br2. It's again another diatomic. And all of these are going to stay aqueous, and we can see the difference here in the colors. Okay, what is this one? Sodium chloride. Oh, yes, NaCl. Okay. And then in this other example, it's the same kind of deal. Chlorine is more active than iodine, so we can, again, displace this iodine, and we can get iodine, and again, sodium chloride. And iodine's also a diatomic. And when we look at the picture here on the right, here we have on the very bottom what I believe is chlorine. And then on the top is the bromine. And then here on the bottom, this is, it looks orange, but it's like it's yellow mixed with some purple. So this again is chlorine. And then the top, we have the iodine, which is a very rich purple color. Cool. So I guess I do kind of want to talk about metals and acids. So let's give one example of a metal and an acid. Say, for example, we take copper and I put in HCl. And I'm going to quickly look this up because, actually, we can look at the activity series from lesson 15. We can kind of jump ahead a little bit. How about we do a different example? How about we do potassium? So if I take potassium and I place it in a solution of hydrochloric acid, here we have hydrogen plus a nonmetal. We're going to end up displacing the hydrogen. So we can end up switching these two, and we'll end up getting a very vigorous reaction. We'll get hydrogen gas that bubbles off, and then we'll get potassium chloride that forms. Okay, so those are three different types of single replacement reactions. And potassium is, when you have a sample of pure potassium, it's a solid, and then hydrochloric acid would be an aqueous solution in water. So, okay. Now let's look at three different types of double replacement reactions. So when you have a double replacement, again, if we look at the diagram, we're going to be replacing the cations between two different compounds. And part of the fun parts about chemistry is predicting whether a reaction is going to occur or not. And this takes years of experience to kind of to get down. But there's a couple things that we can start to predict very quickly. And all based upon whether the reactions are going to be soluble or not. And I'll talk about that in lesson 15 and 16. So for a double replacement where we have a insoluble compound that comes out, we call this a precipitation reaction. And we can see an example of this here on the right. I have potassium iodide, which is in this burette. You can't see the burette, just the tip of it. But it's being titrated into a solution of lead 2 chloride. And so lead 2 chloride has the formula PbCl2 because lead is Pb2 plus and chloride is Cl minus. So we're going to get PbCl2 as our formula. And when these two compounds come in together, the potassium and the chlorine are just kind of side products. They're spectator compounds. But the lead compound and the chlorine are going to react together to form a solid compound. And that comes out as this yellow precipitate that's going to kind of look kind of bubbly at first. It kind of turns into this goo, and then it settles at the bottom of the Erlenmeyer flask. So that is going to be our precipitate, and it is going to be lead chloride. Lead iodide. My bad. So that's a solid. So when we write this out, you might not know what the products are right away. So all you need to do is exchange these two. And so we'll end up getting lead 2 iodide. And this we'll be able to predict in a little bit is not aqueous, but in fact it's going to be a solid. And then we'll end up getting potassium chloride as another product here. Potassium chloride is aqueous, it's soluble, so it's going to stay in solution. So that's another one of these compounds that's in here, we just can't see it. So in chemistry, what we're looking for is changes, and the change that's occurring here is a precipitate that's coming out of solution. So let's go ahead and write this formula out. So potassium iodide, and I keep wanting to write P for potassium. It's K, got to remember that. Ki. And then we have PbCl2. And we're going to get lead 2 iodide, which is PbI2. And that's a solid. And then we're going to get KCl, which is aqueous. And then to balance this reaction, we'll need to we'll need to make sure we have the correct number of halogens. So there's 2 iodines on the right side, and there's 2 chlorines on the left side. And if I put coefficients of 2 right there, everything is balanced, so we don't need to make any more changes. A lot of times when you go to balance a precipitation reaction or a double replacement reaction in general, you want to make sure that you have the formulas correct, because if you don't, you'll end up in a perpetual loop of not being able to balance it correctly. All right. Another type of double replacement reaction is a neutralization reaction, where we take a compound called an acid and a compound called a base, and then we mix them together. We'll get a salt, and then we'll get water as a product. And we can monitor the progress of an acid-base reaction by using a pH indicator. And here on the right is a acid that's being titrated with a base. And as the pH increases, as it becomes more basic, the indicator changes color from colorless to a magenta. And that tells us that we've reached the neutralization point, which in this case is 7.0. The indicator actually changes a little bit higher than that. It's around 8.0, but nonetheless, we can see that the reaction has become neutralized, meaning we've formed water, and we have removed all the acid, removed all the base as much as possible. We've gotten close to a pH of neutral, which is 7.0. We don't really talk about acids and base chemistry that much in general chemistry 1. Weirdly enough, it's held off until general chemistry 2, but we can talk about some of the basics here. Perchloric acid is a strong acid, and we'll talk about the polyatomic down below, but if we look down here, we kind of jump ahead. Perchlorate is gotten the formula, whereas perchlorate, right here, ClO4 minus. So if we just go ahead and add a hydrogen to that, we'll get perchloric acid, so HClO4. And calcium hydroxide has the formula of CaOH2. Hydroxides have the formula of OH minus. And so calcium with a 2+ charge will make the formula CaOH2, because we're going to need to have 2 hydroxides to cancel the charge on 1 calcium. And so this could be the acid here. It could be perchloric acid. And then here in the burette, we have calcium hydroxide. And then the pink is the indicator that's changing color. So if we can't notice a physical change from the reaction that we're monitoring, we can have another reaction that has a color change, such as an indicator. And this one's due to pH. And there's lots of different pH indicators that exist. In the red cabbage lab that you did last week, that was the anthocyanins that are in the red cabbage that change pH and give you a variety of different colors across the pH spectrum. Okay, and then the salt and the water that form, well, water is just water, so H2O. plus water. But the salt that's going to form is the anion and the cation combining together. So we'll get calcium perchlorate. So we need to name it with the polyatomic here. So we're going to change the ending here, and I'll show you how that works in a little bit. So calcium perchlorate, this is going to be aqueous, and then water is always going to be a liquid. So we can finish writing the reaction as Ca perchlorate, ClO4, and perchlorate has a -1 charge, so we'll need 2 of those. And then we'll have water, so liquid. And then this, I'm not sure, is this balanced? No, it's not. So let's go ahead and balance it. We'll need 2 acids for every 1 base, because this base here has 2 hydroxides with it. And as a result, we'll end up getting 2 waters that form here. Okay, we can see that if we just look at this as 1 unit here, okay, so I have 2 of those units on the left and 2 now on the right. And I look at these hydroxides here, there's 2 oxygens from those hydroxides, and those end up right there. It's a little hard to see, but you can go through and you can balance that one. You want to treat the polyatomics as if they're a single element when you're balancing it. So if you go to set up something like this in terms of balancing, you have your left and you'll have your right side. And what I like to do is on the left side, I'll list the ClO4s on the left. I'll list the calciums. I'll list the hydroxides. And I guess we can list, I think, yeah, I mean, it's a little tricky. You might list the oxygens separately like this. So we have 2 chlorates on the left and 2 on the right, 2 calciums on the left, 1 on the left and 1 on the right. And then for the oxygens here, there's 2 here, and then there's 2 over here. So from the water. So, okay. The last type of double replacement reaction are ones that form a gas as a product, and then sometimes that gas will go on to react further. And these are the 4 types of gas reactions that you want to be familiar with. So you can get hydrogen sulfide, that's a product. We can get sulfurous acid. And if you form sulfurous acid, it will break down to sulfur dioxide and water. If you form the product dihydrogen carbonate, you end up getting carbon dioxide and water as a product. And then if we have ammonium hydroxide, that always breaks down into ammonia and water. So those are the only 4 that you need to be familiar with. And then for this reaction, I have limestone. And if I take limestone in the field and I take a little bit of hydrochloric acid and I put it on the limestone, we'll end up getting a bubbling reaction that occurs. And then this is a good test for if we have some limestone, because some rocks don't react to acids and some do. So in this case, we need to know what the formula for limestone is. And limestone is calcium carbonate. And carbonate, CO3, is another polyatomic ion we'll talk about here, which has the formula of, where is it? CO3 2-. Okay, and then hydrochloric acid is hydrogen with chlorine. And here limestone is a solid, so let's go ahead and indicate that. Hydrochloric acid is an aqueous solution. And then what we're going to do here is we're going to exchange the cations. And when hydrogen combines with carbonate, we end up getting dihydrogen carbonate, which is got the formula this H2CO3. And then we can get, what is the other formula? Calcium chloride would we get. Okay. So calcium chloride. Now, one thing to keep in mind here is that the dihydrogen carbonate here is going to break down further. So we can see that it's right here. So that the reason why this bubbles here, so we have the bubbling that's occurring, this is from the carbon dioxide that's produced. So this is going to immediately break down and form CO2, and we're going to get water. Okay, so the overall reaction is calcium carbonate reacting with hydrochloric acid to give us carbon dioxide, water, and calcium chloride. And we do also want to balance this reaction. So let's go and try to do that. So as we can see here, there's 2 hydrogens that need to combine with carbonate. So we're going to put a 2 here. And then the right side's good here. And everything else looks good. So there's just, we need a 2 there. Cool. And then the last type of reaction I want to introduce is the combustion reaction, which is one of the more useful reactions that we use on a daily basis whenever we're heating our homes or powering our cars. Here's a simple one where if you take an ethanol-based lamp, say for example you're at an Italian restaurant, they have one of these on the table. Inside here we have a fuel. This is ethanol. There's going to be a little bit of water here as well. But that ethanol is going to combust with the oxygen to give us carbon dioxide and water. And as this puts off a lot of energy, it creates a fire in the process. And ethanol is a organic-based compound, so it's going to have something of the formula carbon and hydrogen, but ethanol also has oxygen in it too. So the formula of ethanol is C2H3OH. Oops, that's not right. C2H5OH. Another way that you'll commonly see ethanol written is C2H6O. The reason I'm not going to write it that way is because this is the proper way to write it in terms of organic chemistry. We want to indicate that there's a hydrogen attached to this oxygen. If we were to draw out the Lewis structure for this one, it would look like this. And that's why it's written as OH, helping you determine that there's a hydrogen attached to an oxygen. All right, so when this comes into contact with oxygen and a spark, we're going to end up creating a carbon dioxide, and we'll get water vapor as a result. And I say water vapor, I mean water is in the gas form. And sometimes we'll write these reactions for combustion reactions where this is also listed as a liquid. And that's important if we want to know exactly how much energy is output. So we do have to pay attention to that as well. Maybe if you're doing the homework and it gives you the wrong answer, maybe they want it as a liquid there. Okay, so one other thing we got to do, of course, is to balance this reaction. And balancing combustion reactions, the strategy is to balance the carbons first, and then you want to balance the hydrogens, and then the oxygens last. So let's go and do left and right side. We have carbon, hydrogen, oxygen. On the left, I've just balanced it so that the carbons are both at 2. On the left side, we have 5 plus 1 here. And I'm going to just combine that to be 6. So there's 6 hydrogens on the left. And on the right side, there's currently 2. So what I'll need to do is put a 3 here. That'll give me 6. And then how many oxygens do I have? Well, I have 2 times 2 is 4, plus another 3 here. So that's going to give me 7 on the right side. And then on the left side, we have 3. We have 1 plus 2 from the oxygen here. So 1 here, and then there's 2 of them here. So if I want a total of 7, we're going to need to put a coefficient of 3 right there, so that we end up getting a total of 7. So 1 plus 6, which is, of course, 7. All right, so combustion reactions can be a little bit tricky to balance, especially when there's an oxygen here. But that's why I wanted to give this as an example for you to practice. Okay, so let's go and finish off today's lecture with talking about naming, specifically when it comes to polyatomic ions, acids, and hydrates. Now, a polyatomic ion is going to be a compound that consists of 2 or more atoms that are covalently bonded together and that function as a single charged entity that's stable, especially in solution. So if I have carbonate in solution, CO3, it doesn't break up into carbon and oxygen. It stays as carbonate. So all these polyatomic ions are stable. They can be broken down further, but it depends on what it's reacted with. So unlike a monoatomic ion, which consists of just a single atom, these polyatomic ions have a specific arrangement, and most of them will have oxygen in them, but not all of them. These ions can either be positive or negatively charged. We'll often see negative polyatomic ions as the most common ones. The name of the polyatomic ion refers specifically to the molecular formula that's given here and the charge that's specified. And it's important to memorize a lot of these so that you don't get confused when you come across them. You don't necessarily need to memorize them. Maybe just have this chart here. This is taken from the polyatomic chart of the ions that I gave you in the first week of class. So you can find that there at the top. Hydrogen is also often present in these as well. So if we have hydrogen present, sometimes it'll be listed as hydrogen carbonate. Another name for this would be bicarbonate. The prefix bi refers to one hydrogen. So hydrogen phosphate would be HPO4 2-, and dihydrogen phosphate would be H2PO4-. But sometimes people would just call hydrogen phosphate biphosphate. And I don't recommend that that nomenclature. It's just kind of confusing. So let's stick with the names that are on here. These sulfates have have pH in it. Sulfate is written as SULFATE in American English. So in British English, it's given the letters PH instead. So just keep that in mind. Those are the same thing. Okay, now one thing that we want to make sure that we also know is if we're going to memorize these, we need to memorize the charges that go along with them. And it is a little bit tricky to do this, but there are patterns, and maybe just make some flashcards. I have some on my Quizlet deck. You can just practice going through these. But these polyatomic ions are going to be important if you go on to study biology and especially medicine, because you'll see these listed as indicators in medical charts all the time. So knowing these polyatomic ions is really helpful. Now, when these polyatomic ions form a compound, so that when they're paired with a metal, they are given a specific name that depends upon the formula, that depends upon the name of that formula. So let's just go through and practice a bunch of these so you can get an idea of how to name these. If I start with that first example here, CaCO3. So CaCO3, this is calcium carbonate. And why is it calcium carbonate? Well, it's composed of calcium, and it has the polyatomic ion carbonate, which you can find up here, CO3 2-. All we're doing is combining the metal name with the polyatomic name. Now, what about if we have a metal that has a variable charge? Okay, so here we have CuNO3 2. So NO3, this one is nitrate, and nitrate has a -1 charge. And the copper can be either +1 or +2. We can refer back to our chart of the ions for that. And in this case, it's got to be copper 2 because there's a subscript there of 2. So this is copper 2 nitrate. And if it was NO2 instead, it would be copper 2 nitrite. So it's important to emphasize the suffix whenever you're discussing a chemical with a colleague. You want to make sure that you emphasize that so they know specifically which one you're referring to. Here's an example of one that has a positively charged cation. So the polyatomic comes first. So NH4 is ammonium, and when it ends with the anion Cl, this has got to be ammonium chloride. So here the ending IDE is the same as the anion for chlorine. All right, here's another interesting one. I have aluminum, and it's paired up with this very large polyatomic. This polyatomic is acetate, and aluminum is a fixed charge of +3, so that's why there's a subscript of 3 here. So this is just aluminum, so you name the metal first, aluminum or aluminium, you can name it either way. Aluminum acetate. So not aluminum triacetate, not copper 2 dinitrate. There's no prefixes that are added on top of any prefixes that are already given for the polyatomic name. So you have to be paying attention to the charges when you write these out. Acetate can also be written a different way. So sometimes you'll see acetate as CH3COO or CH3CO2, both with a minus charge. So that has to do with the organic nomenclature. Acetate has the formula, the polyatomic formula, the Lewis formula, like this. Getting all these formulas mixed up. All right, so that's the Lewis structure of acetate. So there's a couple ways that they'll write it out. They're all equivalent. All right, how about the reverse way? So let's say we have sodium phosphate. So if I want to go and what did I just do? There we go. So if I want to go the opposite direction, so here I have sodium, that's Na plus, and phosphate, we go and look that up in the polyatomic table. We see it. It's right here. It's PO4 3 minus. So the charge here is really important that we emphasize that it's a 3 minus charge, because when we go to write this out, the formula, it's going to be Na with a subscript of 3, PO4, because we're going to need 3 positive charges to cancel out the charge on a 3 minus charge for the phosphate. So here's our formula for that one. Sometimes you won't find the polyatomic that you're looking for on this chart. There's a variety of other ones that that didn't make it to this short list, such as sodium phosphite. What we notice here is that the ending ATE and the ending ITE refer to the number of oxygens that that polyatomic ion has. So sodium phosphite is going to be Na3PO3. It's just going to have a polyatomic with one less oxygen. We can see that here in the perchlorate series, where we add the ending of ATE when you have more oxygens, but as we get to less oxygens, we drop the ending to ITE, and the greatest number of oxygen is given the prefix of per, and the lowest number of oxygen is given the prefix of hypo. So you'll see that trend here for actually all of them that have a variety of different forms. So that is one way to kind of predict what the polyatomic might be if you didn't know. But again, you can just look a lot of these up. Some of them are kind of tricky, like chromate and dichromate. Dichromate has 7 oxygens, not 8. So it's not what you might expect, for instance. So let's go and do a couple more of these. I have this one, sodium bicarbonate. You see this all the time. But what is the formula of this? So sodium, again, is just Na. And bicarbonate, well, that's the same as hydrogen carbonate. So it's HCO3. So sodium bicarbonate would be Na combined with HCO3. And since this has a -1 charge, we don't need any additional subscripts for that one. Okay, how about potassium permanganate? It's not too hard of a one. Potassium is K+. It's an alkali metal. It's in the first group. And then permanganate has the formula of MnO4-. So because they both have a charge of 1, +1 and -1, you just write the formula as KMnO4. So naming compounds with polyatomics is really not that hard at all. It just requires a little bit of upfront work in kind of recognizing these as polyatomics and not as elements. Another example of this is strontium chromate. Strontium has a 2+ charge. It's an alkaline earth metal. It's in the second group, so it's going to have that 2+ charge. And chromate is CrO4, and what is the charge on that? Well, we go up and look, and it's a 2- charge. So 2- and 2-, they cancel each other out. So when you write this out, it's just SrCrO4. Now, sometimes people write parentheses here, but you really only need the parentheses if that polyatomic has a subscript. So that's why I didn't write any parentheses for those. Okay, so you'll get some practice with that using active chemistry. And there's lots of other places to get some help on this. One place I really like is chemteam.info. If we go to this website, we can find the nomenclature section, and here's some help with polyatomics. So you can get some additional practice problems. I think I pulled some of them from this website, and there's answers for all of these. Cool. Now, to end off the lecture, let's talk about the naming for acids and the naming for hydrates, which you might be a little bit already familiar with from our lab last week. So for an acid, we have three different types of acids based, well, not three different types of acids, but three different ways we can name acids. The simplest is if we have an acid that just has a hydrogen ion and an anion. Whenever these acids exist, so a couple of those would be hydrochloric acid, and hydrofluoric acid, or let's see, iodic acid. All we're doing with these ones to name these is if the anion is going to always end, the anion for these is Cl, which would be chloride. This would be fluorine turned to fluoride. Iodine becomes iodide. We just name the acid with the standard form of hydroblankic acid, where the blank is the anion's root. So hydrochloric acid, hydrofluoric acid, hydroiodic acid, or iodic acid for short. So these are like this first category here. These are the simplest ones. Now, if we have, instead of an anion, but a polyatomic anion, and that polyatomic anion ends in ATE, like we've seen up above, acetate, nitrate, phosphate, then we drop the prefix of hydro, so we don't need hydro anymore, and we just name the acid as blankic acid. So an example of this would be H2SO4. In this case, the polyatomic anion is sulfate, SO4, 2 minus, SO4. And so for this one, we'll call this sulfuric acid, not hydrosulfuric acid, but just sulfuric acid. All right, so let's think about some other ones. How about nitrate when it's an acid? So that would be HNO3. That would be nitric acid. So those are two common acids. We talked about one up above. It was perchloric acid. So what would be perchloric acid? Well, that would be when we have the perchlorate anion. So perchlorate is ClO4 minus. So then that would just be one hydrogen. So HClO4. Okay, so that's how we can go back and forth for these types of categories. And then the last type is if the polyatomic anion ends in ITE instead. So in these, we're going to change the ending to OUS acid, OUS acid. And there's no hydro prefix, again, for these. So we can think about sulfurous acid. Instead of sulfuric acid, this is this one here is, by the way, a strong acid. And so is nitric acid. These are actually, all three of these are strong acids here. But there's a variety of weak acids. And we'll talk about weak and strong acids in a little bit. That means how much they disassociate when you put it in water. But sulfurous acid is a weak acid, and it's got the formula of 2SO3 because SO3 is sulfurous. Sorry, SO3 is sulfite. So because the ending here is ITE, the ending of the acid becomes OUS. And we always have to end it in acid here. And then the last, and then a couple more. Let's talk about, how about hypochlorite? So when we have hypochlorite as an acid, that would be HClO. This is also known as bleach, but this would be given the name of hypochlorous acid. So it goes from hypochlorite to hypochlorous acid. So those are just a couple ways to name acids, and I think it's important to know. So that's why I wanted to talk to you about that today. And then the last type of naming that we're going to do in this class is for hydrates. And again, we've kind of already seen this in our lab. This is just where we have a salt and it combines with water. And those water molecules are in the crystal lattice in a certain arrangement. And every salt has a different number of waters that it can take in. Some don't contain any, and some contain a lot of them. And it's hard to predict actually how many waters a salt is going to take up. But collectively, we call these hydrates. And what we'll do is we'll indicate how many water molecules after, if it's known, with a Greek prefix. So penta being 5. So these are same Greek prefixes when we're naming covalent compounds. So copper 2 sulfate pentahydrate. Well, copper 2 is Cu2 plus, and sulfate is SO4 2 minus. So copper 2 sulfate is CuSO4. We don't need any subscripts there. We'll put the dot symbol that or bullet symbol. This indicates that it's a hydrate, and pentahydrate would be 5. So then we just write 5H2O. And for these, the multiplication, this is not a multiplication symbol. It just means there's 5 hydrates per one formula unit. So when you go to calculate the formula mass of something like this, you just add the mass of 5 waters to the mass of that salt. This portion here is the, if we just had this by itself, like this portion here is the anhydrous, meaning non-water containing portion of the formula. But then collectively, this is known as the hydrate. So if I have the formula BaCl2 dot 2H2O, what would the name of this compound be? Well, first off, we're going to name this portion here. This is barium chloride. And then there's 2 waters, so this would be dihydrate. So it's not very hard to name these, and these come up a lot when we're working in the lab. So there you have it. So there's going to be some problems like this for you to practice on this week's homework. And then in the next lesson, we're going to go into talking more about the reactivity and solubility of these different chemical reactions. This is all chapter 10 in your textbook, and I recommend reading through this chapter. It's a hard one to get through. So there's a lot of different examples, but it's also very interesting. So I hope you enjoy it. And you guys take care, and I'll talk to you in the next lesson.